Okay, so let me recall a little bit where we were last time. So last time we had this category of like light profinite sets. And there are several ways to think about this, either as sequential limits of finite sets or as metrizable, totally disconnected compact Hausdorff spaces. Or as countable Boolean algebras. And we equipped this with the Grothendieck topology. Where it covers are generated by the following two families: finite disjoint unions and all surjective maps. And as I kind of stated last time, this has a very important consequence that I want to stress again, that sequential limits of covers are still covers. And so surjective maps are still covers. This property will actually be extremely crucial in order to have a good, in order for like the resulting theory of like something like topologically being groups that we want to use to have good homological algebra properties. And this is something I maybe want to stress today a little bit, where this appears. And then, okay, so we had this category of light condensed sets, which were these sheaves. Sheaves for this Grothendieck topology on this category of light profinite sets. And in general, whenever you have sheaves on some sites and the generating site embeds, well, at least if it's a subcanonical site, so you have via some kind of Yoneda embedding, you have the light profinite set sitting inside there. So this sends any profinite set S to the functor that takes any t to the maps from t to S, maps in profinite sets. And so if you prefer to think more concretely in terms of compact Hausdorff spaces, this continuous maps t to S. And
the screen is frozen again.
Double question?
Yeah, the screen is frozen again.
The screen is frozen. All right. One important property is that, which is also completely general, is that the image generates under colimits. So you can think of it.
Is it possible to write a bit bigger?
I'll try. So you can think of general light condensed sets as being built out of light profinite sets by some kind of gluing procedure. And then we also had the category of, compared this to the category of topological spaces. In particular, we can embed this here as a certain compact Hausdorff spaces. And in fact, more generally for in topological space, you can build such a thing, and I called this thing I called the topological space A last time. A maps to A underlined, which is given by the same procedure. So you send any S to the continuous maps from S to A. And so this diagram commutes it. And as I also said last time, and I want to make small kind of want to improve on something I said last time. So this has a left adjoint. That takes any condensed set S. To, well, if you have a condensed set, in particular, you have the value on a point, which we think of as the underlying set of this condensed set. And then we were equipping this with a certain topology, right? Here we're taking the disjoint union over all possible maps from the counter set into X, of the resulting map from the counter set onto X top. The reason for the counter set being that it's somehow any such light profile that admits a surjection from the counter set, so it's enough to allow the counter set here. But something which I kind of forgot about, and that Yosoko Morita reminded me after my lecture, is that actually you can describe this differently, this quotient topology, because the counter set, I mean, convergence in the counter set can be detected by sequences, or more precisely, if you map all possible convergent sequences to the counter set, that's still a quotient map. So actually, you can also consider all, I don't know, let's call this beta, all convergent sequences in X of just the convergent sequence. And this is also a quotient map in topological spaces. So if you want the counter set can actually be thought of as the co-limit over all, say, for example, countable closed subsets. So for example, finite unions of convergent sequences. This is in top. It will not be true in condensed sets, and I will discuss this in a second. But it is true in top. And so this means that equivalently you can describe this corresponding topological space as just the one where you just remember what the convergent sequences are. That's enough to determine this topology. In particular, this means that this funny notion that I was talking about of being metrizably compactly generated is actually just the same thing as being sequential. So that continuity can be checked by checking whether convergent sequences go to convergent sequences. And so this thing I said last time, someone now can be phrased more succinctly as saying that sequential topological spaces embed into light condensed sets. Okay. Okay. So from this perspective, it seems that allowing the counter set didn't really help at all. But now I want to say why to allow the counter set.
So is it the same or more general than first countable topological spaces?
I forgot all my general points of topology. Does somebody know? Is sequential the same as first countable?
It could be discrete on huge.
Well,
If it discrete,
Well, discrete things are first countable.
First.
because in the previous version of the theory, it was first countable. I forgot. I think first countable with T1 with all points closed, but now we don't need all points closed because We don't have the set theory
Right.
limit, I mean, bounding thing. So.
So why allow the counter set?
Frozen.
Yeah, we're frozen.
I'm frozen. I hope I'm not frozen. So the reason is that in any topos, so for example, so whenever you have sheaves on any side, there is an intrinsic notion of being compact. And of being Hausdorff. So these are the following notions that I want to recall.
Frozen again.
Frozen again?
Yep.
Oh my God. Um, uh, uh, so this general topotheoretic notion is what's called quasi-compact. If any cover admits a finite subcover. Here, this general notion would amount to saying that there exists a surjection from the counter set onto X.
Or X is empty.
Yes. Thanks. And then there is this intrinsic notion of being quasi-separated, of being Hausdorff. And this notion was introduced by Grothendieck in SJ4. And of course, Grothendieck was using algebraic geometry lingo. So instead of Hausdorff, he said separated. And because it's just a general topotheoretic notion and not the specific separated notion in algebraic geometry, he calls this quasi-separated. So in general, this would say that for all well, maybe I'm assuming here's something about enough quasi-compact objects, but say enough quasi-compact objects, and for all quasi-compact Y and Z mapping to X.
Again. Oh, okay.
Man sieht mich jetzt wahrscheinlich gar nicht gerade, oder? Yeah, okay. So we hope that the technical problems got fixed. Let's see. The fiber product between the two is quasi-compact. And again, let me simplify this here. Again, because on all, you can always project onto any quasi-compact guy by something, by the Hausdorff set. For all two maps from the contour set onto X, the fiber product I should have chosen a notation for the contour set, is still quasi-compact. So this is somehow basically trying to say that, sorry, this need not be surjective, just a map, that if you map a contour set into X, then it may not be injective. So this might be factor over some quotient of the contour set. But you somehow declaring here that it's the quotient by a closed equivalence relation on the contour set, which is one way to express some kind of Hausdorffness. Okay, so in any topos, you can talk about these quasi-compact and the quasi-separated objects. And at least if your topology is finitary, the quasi-compact guys are exactly those where like a finite union of the generating objects projects onto. So if we only allowed for example, the convergent sequence as our basic guy in test category. And the quasi-compact objects would all be quotients of this guy, or at least be countable. So in particular, the contour set would not at all be quasi-compact. And if you want to access the contour set, it would be precisely by such a co-limit. That would be this huge co-limit of smaller objects. And this would mean that the intuition for what a compact object is, like the contour set is very much a compact object and you want that, this would be destroyed if you pass to such a topos. And in fact, I mean, with our notion of what the generating objects are, you in fact get this really nice proposition that, by the way, quasi-compact I will very often abbreviate to QC. I mean, in principle, I hate abbreviations, but okay. This is QC and this is QS, and if both of them are assumed, then these are called QCQS. So you can wonder what are the compact Hausdorff, so to say, light condensed sets. And these are actually precisely the metrizable compact Hausdorff spaces. And if I were to remove light here, I would remove metrizable here. So this means that the abstract topos theoretic notion of quasi-compacity really very closely mirrors the idea of what a compact space is. And similarly, the general topos theoretic notion of what Hausdorff means mirrors precisely what you think Hausdorff should mean. And so this forces basically our Grothendieck topology to be finitary, because otherwise the basic objects wouldn't be quasi-compact. And it forces us to include the contour set in the formalism. And then you can also wonder, more generally, if it drops the compactness hypothesis, but still requires a Hausdorff condition, what are those things? So what are the quasi-separated light condensed sets? And those also can be described in like more standard terms. So we know that the metrizable compact Hausdorff spaces are allowed. And in general, you should think of these guys as being rising unions of quasi-compact subsets. And so in fact, they are exactly the int category where all the transition maps are closed, emergence, let me write injections, really. I mean, all maps are closed. I really care about that they're injective, in which case they automatically close the emergence of metrizable compact Hausdorff spaces. Int, the int category. So, I mean, last time I was talking about the pro category, which were formal inverse systems, and these are formal directed systems. So it's a category like where the objects are functors from a filtered poset towards metrizable compact Hausdorff spaces with all the maps injective maps. And functors, I mean, maps are this usual thing on int objects. Yeah, so yeah, you could also drop the light here and then drop the metrizable here. And let me just point out that within this category, you have what the categories that topologists like, algebraic topologists, called the compactly generated weak Hausdorff spaces. Sorry, metrizably, meaning sequential. But note that they are not the same because in this category, as I said previously, you can write this country set as this huge colimit. Colimit of a countable closed subset. But not in quasi-separated light condensed sets. Light condensed sets. I mean, these are both light condensed sets. I mean, they are both like this is from just the prototypic example of like a int system of metrizable compact Hausdorff spaces. This is also an int system where you just have one term. It's actually somehow a quasi-compact, quasi-separated guy. But as condensed sets, they are very different because this is really just a formal colimit, and this is just one object. And so in particular, this guy is quasi-compact, and this one is not. Okay. But actually, if you ask for int systems that are countable, then actually on such things, this is actually they all come from here. So some of the difference between these two categories only comes when the colimit category is pretty large, as it is in this case.
So I don't understand the subtlety here. So is there a condition on the? So if you take the under this equivalence, the light condensed set, which is the direct limit of the injections of
right.
in the counter set of countable of this
Yes.
only finite unions of images of this sequence space. So is this gives something by the equivalence of categories, which is in this category MCGWH?
It's not an equivalence of categories, right? This is just a full inclusion.
What? What is included in what? Okay. This one is included. Okay. I didn't realize that this is what you were saying. Okay.
All right. Let me just say something that's implicit in one. Is that we said in particular like something very nice like the interval. It's definitely a nice metrizable compact Hausdorff space. We said it should be quasi-compact as a condensed set. And I said that quasi-compact, I just erase it, quasi-compact means that there must be a surjection from the counter set. And in fact, that is true. You can find a surjection from the counter set. And in fact, some kind of canonical one. I mean, so if you have a sequence A0, A1, A2 of either zeros or ones, you can sense this to the number in binary 0.A0, A1, A2, the binary extension. Which is an element in the interval, and any point in the interval admits such a representation, and so you get this surjective map. But we definitely need the counter set or something as large as a counter set to surject onto here. And so you can then recover this whole guy by as a certain closed equivalence relation here, where the equivalence relation is precisely this nasty thing that 0.11111 is the same as 1.002. So. All right. Okay. Okay. So, but I mean, we're mainly interested in this formalism of this light condensed sets as a framework for doing some kind of algebra where all the objects have something like a topology. So, and to get this started, let's talk about light condensed being groups. So I already started this last time, but just very briefly. So we have this category of light condensed being groups. There are actually two ways to think about this. Didn't say it last time. So either these are being group objects in light condensed sets. Or these are sheaves of the being groups. Let me just write in simple. So sheaves on this category of light condensed sets with values in the being groups. And similar remarks apply to any kind of algebraic structure. So if you have condensed rings, for example, these you can consider them as ring objects in light condensed sets or as sheaves of the rings. And I mean, just from the general theory of sheaves, of sheaves of topoi, we know that this is a abelian category, in fact, a Grothendieck abelian category, so filtered colimits are exact. It also has a tensor product. So actually, let me describe a little bit what the properties are. So the unit object is just the underlined. So this thing, I mean, the thing associated to the integers as a discrete thing. And if you have two guys, then M tensor N is a sheafification of the pre-sheaf that sends any S to the tensor product. Right, so I mean, this is just some functor from light profinite sets to being groups. So what's called pre-sheaf, and then you can always sheafify and force a sheaf X in.
Frozen.
Oh no. And there's this further property that I want to stress, which is also completely general. So if you have a light condensed abelian group, then you can forget the abelian group structure and just have an underlying condensed set. But this has a left adjoint. Some kind of free construction, so the free condensed abelian group. Let me drop the light when I say that. That takes any light condensed set to the free abelian group on X, where Z adjoint X, I mean, in general for these like colimit type construction like tensor product and such a left adjoint, you always have to sheafify. So it's the sheafification of the thing that takes any S to the free abelian group on X. So this is already some structure that at least you don't often think about in topological abelian groups. So you don't really often take the free group on a topological set, I mean, in topological space. Here it exists and it's actually a completely fundamental structure. So the idea is that this guy is some topology on like, I mean, what is the underlying group of this? It's just the free guy on X of star. So if you have any kind of topological space, you can just take the free abelian group, of course. And then this machinery will put some kind of topology on the free abelian group. Let me actually discuss this in an example. Yeah, sheafification won't change the value on the point. That's just because any cover of the point is split. And so the sheaf condition is kind of vacuous on the point. Yeah. Yeah, so here's an example. Let's contemplate, which is kind of related to the introduction I gave last time. We can now take the real numbers, and very soon I will forget to write the underline all this time because implicitly everything has become a condensed set. But okay, so we have the real numbers as a condensed set and then take the free condensed abelian group on that. So what kind of object is this? So it's somehow sums, if you want, of real numbers weighted by some integers, where nx is an integer and they're almost all 0. So you might think of these guys represented by x maybe as, I don't know, Dirac measures, and then these are finite sums of Dirac measures or something like this. But now it also has some topology where you kind of remember that, I mean, this x is allowed to somehow move continuously, but then you can have x minus y. In general, that's a non-zero element, but then when x and y become the same, then suddenly this collapses to right, and so maybe it's apparently not so clear how you would actually describe this topology. Like, what are the open? If you would want to describe this as a topological abelian group, you would have to declare what the open subsets are, and I think it's a little bit tricky to concisely say.
Frozen again.
Frozen again. But you can actually say what it is as a condensed set. So first of all, because this free construction commutes with colimits, this is definitely the colimit over, like, I don't know, all intervals minus c to c in R of the free guy on an interval. And I'm doing this because now this has a nice feature that it's now compact again. And the C adjoint I itself can be written as a rising union over all integers n of subsets where you are only allowing a signed sum of at most n elements. So these are sums x and I, nx times x, where the sum of the absolute values of the n-axis is at most n. Right? I mean, everything is contained, they're almost all 0, everything contains something like this. It is also true as condensed set. So whenever you have a profile set mapping into here, it will actually factor over one of these subsets. And these guys, these guys are compact Hausdorff and metrizable. And it's a kind of fun exercise to figure out how to describe this compact Hausdorff space. So I claim that whenever you have any compact Hausdorff space and you look at finite integer value sums of points of them, where the sum of the coefficients of the values at most n, there's a canonical compact Hausdorff topology on that. And I think classically this takes a little bit of thinking. I mean, in this formalism, this free construction just produces it for you automatically. And some of the subtle part of this is that there are some kind of non-trivial identifications you have to make, right? So in general, you have x minus y, and that's a non-zero element, but then when they become equal, you have to collapse this to 0. And so actually to make this true, you actually already have to use quite that in our Grothendieck topology, we didn't just allow finite disjoint unions, but also surjective maps. Otherwise, this wouldn't come out right. And so also by general nonsense. If you start with something that already had a group structure, then if you pass to the free guy, this now has a ring structure where the multiplication comes from the addition here. So in particular, this is actually a condensed ring, completely naturally. And this is kind of related to this question I had in my first lecture. Like, how do you join an element in all its real powers? And it's just done by this construction. All right. So this is like, these are general features, and now I want to mention a few features that are quite specific to this light condensed setting. The first thing is that countable products are exact. Now, this might seem like an operation you're maybe not so often doing, but something you are certainly very often doing when you do some kind of function analysis is to take sequential limits of surjective maps. And they are still surjective. So for example, in function analysis, maybe you have some kind of Fouché space, and it's a sequential limit of Banach spaces. And maybe in that case, its transition maps are not even surjective, but it will also come out right. But definitely you want to take such sequential limits. And for example, if all the transition maps are surjective, you definitely want it still to be, I mean, you want sequential limits to behave nicely. And as I will argue in a second, this actually more or less forces you to go, that your basic objects that define your site must be some kind of totally disconnected things. So you have these, and there's this other property that I will explain what it exactly means in a second. So you have the sequence space. It's a light profinite set or light condensed set, and you take the free guy on that, and this turns out to be internally projective. Recall that one way to say what projective means is that, I mean, in any Grothendieck abelian category, you can define X groups. It means that Xi, so T is projective if X is 0 for I bigger than 0. And it's internally projective. So this makes sense when your category also has a tensor product. Because if you have a tensor product, then you can define an internal X group. And internally projective means that's the internal X 0. And so the first two properties are actually things that are better in all condensed abelian groups because they are all products are exact. And, well, okay, this is also certainly still true. The third property, however, is something that's only true in the light setting. Let me define the internal X. So basically, if you have a tensor product, then you can also ask for an internal hom, which is some kind of adjoint of the tensor product. And similarly, the internal X will be some of the same thing on X groups. Okay, so let me prove this actually. Let me first note that 1 reduces to 2. So taking products, the only thing that's not true for general, like the product of injective maps is always injective, and so on. The only thing that's not clear is that the countable product of surjectives is surjective. So we need for all sequences fn from some mn surjecting onto some nn, also the product of the fn's from the product of the mn's is surjective onto the product of the nns. These are all surjective, and this is surjective. But you can actually write this in the following funny way. So for all m, you can take the product over all n at most m of mn, and then the product over n bigger than m of nn. And this surjects onto the product of the nn's. Because finite products, there's the same thing as finite direct sums, they are always preserved surjective maps, they're always exact. And so you can always, like infinitely many coordinates, you can kind of do the lift. But then this guy here, I mean, this map is the limit now over m of these things. And so we've written it as a countable limit of surjections, and somehow enough to prove that this is still surjective. And so for 2, so assume you have such a diagram. So you have M0, M1, M2, and M infinity is the limit of this diagram. Which certainly maps to M0. And we ask ourselves whether this is surjective. So what does it mean to be surjective in the sense of sheaves? So this means that whenever you have one of your objects generating your site, so any light profinite set, and a map from here, then, well, if it was a surjection as pre-sheaves, then you should immediately be able to lift that to here. But in fact, it's enough to find a surjective map from some, let's call it S infinity. And a lift to here. So does there exist some other light profinite set surjecting onto S and a lift to M infinity? That's the question. That's what the surjectivity unravels to. But let's just see what happens. So we definitely, well, right? So this is map to M0. But we know, because this map is surjective, we know that there is a light profinite set and a lift to here. And then again, because this map is surjective, there exists some further light profinite set and a lift to here.
Subjective, okay.
And so now you can just take S to be the limit of this diagram. So inductively, you construct light profinite sets with a map to here. and then takes a countable limit of these surjective maps. And as I said last time, and I think I recalled today, countable limits of surjections are still surjections in light profinite sets. And hence, this guy is still allowed as a cover in our Grothendieck topology.
So in the definition of your X group in the shapeification, you drop the underline on the left board. So Z of S, you mean Z of S underline?
Yeah. Let me drop the underlines. Okay, so S is for me a light profinite set, and they fit via Ionida inside of light condensed set. So yeah, if you feel better to make an underline. I mean, yeah. Like the Ionida embedding has no decoration for me. It's just the same thing. But yeah, also in 3, like this 3 guy it's like maybe I should also underline that union. Okay, so before I go on to the proof of 3, let me reflect a little bit on what happened here. I mean, so this is this finishes 1 and 2, and let me come back to 3 in a second. So here's really the critical thing. So we definitely for doing good homological algebra, as a lot of function analysis kind of homological algebra, you definitely want property 2, yeah. But critical for 2 was exactly this property that countable limits of surjective maps are still surjective. Countable limits of covers in your Grothendieck topology are covers. And I claim that this basically forces you to use totally disconnected spaces as a building blocks. Why? So you might also have the idea, and I think people are doing that, that if you want some kind of nice category of something like topological real vector spaces, you might work in this kind of smooth setting where you take your defining side to be like smooth manifolds, and Grothendieck topology be just the usual one of open covers of smooth manifolds. But in that case, this will never be like this property that countable limits of covers are covers is just not true, right? Because if you have like maybe just like I don't know the real line, then you or just like a small interval, then you can cover it by 2 intervals. Each one of them you can again cover by 2 intervals, and then keep doing. But then the intervals shrink and shrink and shrink, and in the limit, all you've left is this cloud of dust, which is a counter set. So like even if you start with some nice spaces like some interval, and then cover this by 1 interval and another interval, and then cover it by smaller intervals. In the limit, we get something totally disconnected. And of course, the limit, it doesn't have any reasonable sense of a smooth structure anymore. And so like, I want to claim that this basically forces you to take, right, as your building blocks, basically totally disconnected compact Hausdorff spaces. And initially we took all of them. We realized it's slightly better to restrict to symmetrizable ones, and to have all surjective maps as covers. Because you can actually show that any surjective map, like of light profinite sets, can be written as a sequential limit of actually open covers. So if you want open covers and their sequential limits, you need all of them. And actually, I should maybe say that this is not some kind of ahistorical comment, but this Proital topology was in fact first, I mean, so this stuff about condensed sets, this comes from something called the Proital topology, like original empiric geometry and then in for schemes. And there the wish was precisely that limits of surjective maps should still be surjective, because this was, we wanted to have certain sheaves which were naturally certain inverse limits, and we want them to be well behaved. And for this reason, we allowed these countable limits, or all limits of covers, to be still be covers. So this is really the origin of this whole theory. All right. So this was a small interlude.
So, excuse me. So if you have a map of surjective map of light profinite set, for example, you take the n union infinity, two copies of n union infinity. So all of the two sequences will converge to infinity, and then this is covered by two copies of n union infinity, and they intersect at infinity. So you say that this surjection is in some sense a limit of open. You made a statement to the effect that
well, okay, not all transition maps are surjective, but actually, you know, I mean, actually something slightly stronger is true. I don't need all the transition maps to be surjective. I only need that the maps down to S are surjective, and the limit is still okay. And in that sense, you can write it as a limit.
Okay, in this other sense, okay.
Something slightly weaker would be, yeah, I'm not, I would have to think how much difference this makes. Okay. So I want to prove this thing, that this is internally projective. But before I do that, let me make a warning that this is a phenomenon that's only true once you pass to groups. So n union infinity is not at all projective in light condensed sets. And I actually kind of expected Gabor wanted to go there with this remark, because this is precisely the example that I now need to do. So you can have a surjective map of light profinite sets and a convergent sequence downstairs, so that there does not exist a lift. And one example for this would be to just take this to be the convergent sequence itself, and this to be, like, I don't know, 2n union infinity disjoint union plus 1 union infinity. So I'll break up infinity as like the limit of the even guys and the odd guys. Then, like on the integers, you only have one possible lift, but the even guys converge to something else than the odd guys. But miraculously, once you pass to groups, it so happens that if these were light condensed being groups, in fact, you don't need structure, then any convergent sequence can be lifted. Right. Let me actually use a slightly different guy. So let M be the free guy on the null sequence. So you can take n union infinity and mod out by p times infinity, which is actually a direct factor. Right, because you have infinity mapping here and then projecting to a point. So this splits actually as a direct summand. And so, and of course, the integers themselves, they are projectives. That's okay. So the question is really whether this other part, so this classifies null sequences. So mapping out of M is the same thing as giving a null sequence in the other guy. Or in other words, it's a free condensed abelian group on a null sequence. And free guy on a convergent sequence, but then the limit point should be 0. So if we want that this guy is internally projected. And let me actually focus on the projectivity and then just at the end say a few words why it even works internally. All right, so let's call them A and B because I've already used them. Oh no, let's call them until that projecting down to n. And I have this map from so n tilde to n is a surjective map of light condensed abelian groups. And we have a null sequence in n. And we would like to lift this to n tilde. So this is the projectivity. All right, so let me draw the diagram again. So you have n union infinity here. It maps to n. We have n tilde here. So this maps and with the property that infinity goes to 0. But because this is a surjective map of condensed abelian groups, this means that there is some surjective map from a light profinite set that lifts to n tilde. That's just what the surjectivity means. Okay. Now, how do covers of n union infinity look like? So n union infinity is like you have a discrete set and then it accumulates towards infinity. And now in a priori you have like some complicated S upstairs here. But you can always make that smaller because for each of the discrete points here, you can just pick any lift. I don't know. I don't care which one. And then all these lifts together with keeping everything at infinity. This is a closed subspace, right? So there exists S prime, a closed subspace, so that over here, so you just pick one lift here. so that S prime, the fiber over just the integers is just always a point, right? So you can assume that this S here is somehow a different compactification of N, right? So, without loss of generality. I mean, we can always make S smaller here, right? This is as long as it's still surject, so we can assume that S, the part over any finite thing, is just a point. Okay, but there are many, many compactifications of the natural numbers, and so we, for example, this one, so we can expect that we can directly split that. But now we actually use a property of light profinite sets that I mentioned last time. Okay, so let S infinity be the fiber over infinity. So this might be some big thing. So there's a certain closed subspace in S. But everything here is light. In particular, S infinity is light. And I stress it here because here it's really the critical point where lightness is used. And this means that it's injective in profinite sets. All profinite sets even, but in particular in sequential profinite sets. It's also non-empty if Gabor wants to ask that. And so there exists a retraction. R from S back to S infinity. Okay, so let me call this inclusion here I mean, maybe this was my original map F, and this was a map G. Okay, and now we can just write down the lift. So now consider the following map. Well, a priori it's a map from S. Consider the map from S to N tilde, which is the map G that we had. But then from it, you subtract what you would get if you first go use a retraction and then well, then re-embed into S and then apply G. So if you look at S infinity, then on S infinity, these two maps are just the same because this was a retraction. So S infinity actually. Am I frozen again? So S infinity actually just on S infinity, it's a constant map 0.
Again. Frozen.
Is there a question?
Frozen.
Frozen again. Do you see me now?
Yeah.
Okay. But so S surjects onto N union infinity. And this maps to infinity. And because this is actually a surjective map here, you can actually show that this is a push out in light condensed sets. And that's basically a version of this gluing condition that I gave to, if I want to, so what does it mean that it's a push out? It means that whenever I want to give a continuous map from here to somewhere, it's enough to give one here and here, which agree on the overlap. But it's definitely enough to give one here. And then the question is just, when does it descend down to n union infinity? This means that on fibers, it must be constant. But there's only one fiber in some sense where there's something to check, which is the fiber at infinity. And there we precisely assume that it all just comes from a point. Okay, but so now you're precisely in this situation. You have a map from S, you have a map, well, the zero map, and they agree on here. So this means that actually this whole map factors over a map from n union infinity to here. And let me call that map here basically F tilde.
Awesome.
Oh my God. Okay, and now we basically have all the structure we need, and we just need to check that we actually produce the lift. So what do we have now? Now we have a map from n union infinity to n tilde, which vanishes on zero. So in other words, we've precisely produced a null sequence in n tilde. We still need to check that it lifts the original sequence.
So what is the map G?
Maybe you don't see it anymore. This one. So on S, I can find the lift. That's my map G.
So on the top row, you compose G with R or something? S
Right.
to N tilde.
First, so I have the map G. And the other thing I take is I first do the retraction and then apply G, or, well, I go back and then apply G. That's what this map here is. And then I take the difference. And the difference is just 0 on the closed subspace as infinity, because this was a retraction. And so this means that that because of this push-out property, that actually you really get a null sequence.
Mhm.
Okay, so you have a map from the convergence sequence modulo infinity to n tilde. And now the question is whether we've actually lifted F, and the claim is that we did. To check that we did, note that this guy here is still surjected on by the free guy on S. So to see that this map here is F, it's enough to check for the composite. And the point is that if I take this thing that I used here as a correction term and I project that down to n, then this is this map from S to n. This vanishes on all of S infinity. So this term projects to 0 in n. right? Because this composite map from S to Antilla to N, this vanishes on S infinity. And so the correction term, it vanishes, and G was a lift, so we're fine. And for internal projectivity, I mean, yeah, let me not do it. I mean, it's essentially the same argument. You just have an auxiliary profinite set floating around that you also need to cover a bit. And again, it's critical that sequential limits of surjective mass are surjective. All right, here's just one remark. So the comparison to all, about the comparison to all condensed abelian groups. This is something that I already said orally a bit, but just say it more explicitly. They're all products are exact. And you have projective generators. C adjoin S, where S is what's called an extremely disconnected set. So for example, it's a Stone-Church compactification of some discrete set. These are huge things. They are of cardinality 2 to the 2 to the cardinality of I. So one thing that's better there is that you really have projective generators. You don't have projective generators in light condensed abelian groups. You have this one guy, which is a free guy on a null sequence. But the free guy on a counter set cannot be covered by a projective object. This is slightly unfortunate, but actually not that bad in practice. I mean, the good thing is that in light condensed abelian groups, you have this really explicit projective object, which is a free guy on a null sequence. Whereas here, these projective guys, they are just, I mean, they exist, but they exist by the axiom of choice. But these Stone-Church compactifications are completely inexplicit, and their precise structure depends on which model of set theory you're working with, and so on. But one thing I want to point out is that none of those projective generators there, but none of them are internally projective. So basically, if you take, I mean, this would amount to the question whether if you take a product of two Stone-Church compactifications, and I and J are infinite to exclude trivialities, then this is never projective. That's actually not so easy to see that it's not, but we can prove it. And this is actually a rather severe technical issue in the category of all condensed abelian groups. So it's extremely nice that you have these projective guys, but for many arguments, you would really like to know that they are internally projective, and they are not, and that's bad. And in light condensed abelian groups, at least we have this one really nice internally projective object. So that's good. Right, and the other thing I wanted to point out explicitly, it was kind of implicit in what I said already, is that this is not projective in all condensed abelian groups. So the light ones embed into all ones, and you could ask whether it's still projective there, but there precisely the Stone-Church nonsense gives you obstruction. So you can I mean, some of the universal compactification of the integers is, or the biggest one is the Stone-Church compactification. And this surjects. And you can show that there does not exist a splitting here. Maybe another thing I should say is that this is also related to certain questions about Banach spaces that people have studied in the literature. So they're the only known injective Banach spaces. So there's some kind of duality that what used to be projective in this condensed stuff will become injective in the level of Banach spaces. Are continuous functions from some S into R, where S is one of these extremely disconnected guys, which I could have also allowed. So basically, such a Stone-Church compactification or a retract of it. And it's known that all injective Banach spaces, they are retracts of continuous functions on a Stone-Church.
What about injective? So in your case, it is for Lighting, it's a Grothendieck category, so it has enough injective. But for all condensed, there is.
There are no non-zero injectives in all condensed ones. In all condensed abelian groups, there are no non-zero injective objects.
Okay.
Yeah, they exist for set theoretic reasons. I mean, for like general nonsense reasons in light condensed abelian groups. But I don't think you can write any of them down. And what corresponds to this free-Gaussian null sequence is the Banach space of the null sequences. And this is not injective as a Banach space.
Frozen.
Frozen. But it is what's known as separably injective. Where you only test this injectivity against separable Banach spaces. And this is very much related to this thing that this guy is not projective in condensed abelian groups, but it is in light condensed abelian groups. And actually, I think I made this realization that it is projective in light condensed abelian groups after looking up this proof that this guy is separately injective. And actually, it was an open question in the Banach space literature whether the continuous functions on this guy is a separately injective Banach space, and in the notes on complex geometry can kind of prove that it's not separate, not even separately injective. And in particular, this guy is also doesn't behave like a projective object even when you test against light condensed abelian groups. Anyways. I mean, maybe one thing to take away here is that you might think that all this totally disconnected nonsense shouldn't really appear when you do like function analysis over the reals. But actually, those people that studied like quantum spaces intensively, they are very much studying like continuous functions on totally disconnected things. So, okay. Right. Yeah, maybe let me finish the lecture by talking about cohomology.
You also said something I forgot when about in which context about the axiom AB6 of abelian category.
Yeah, right. Yeah, so in Grothendieck's Tohoku paper, you can find a lot of axioms that a abelian category might or might not satisfy. AB5 is the question whether all products are exact. And this is true in all condensed abelian groups. It's not true in light ones, but at least the countable ones are okay. And then when AB5 is satisfied, you can ask AB6, which is a certain question about the commutation of infinite products with filtered colimits, which always sounds confusing, but you can actually make a statement that's true. And this property, I mean, this is always true if you have enough projective generators. In particular, it's true in condensed abelian groups. And if you restrict this question to countable products, then it's also true in light condensed abelian groups. So yeah, so AB6 holds for countable products. In light condensed abelian groups. And one way to see this is that you have this fully faithful embedding of light condensed abelian groups into all condensed abelian groups. This commutes with all colimits and it commutes with countable limits. So in particular, these countable products, they are some of the correct products. They are the ones that you would also compute in condensed abelian groups, and there this holds. But you can also just check it by hand. Right. So in the last bit, I want to talk about cohomology. So when you study topological spaces, you probably also care about the cohomology. In particular, like for manifolds, you would want that to be the singular cohomology, right? So we have like when you think about topological spaces, we already have an idea what the cohomology should be. Just as like we already had an idea what a compact thing should be, right? And so on and so forth. But on the other hand, whenever you work in a topos, the topos somehow comes with its preconceived notions of, well, what compact objects are, but also what cohomology is. And so if X is any condensed set, and say M is any abelian group, it could even be a condensed abelian group, but let's restrict to like discrete ones for the moment. You can define the cohomology of X with coefficients in M. And this is just something that is just there whenever you work in the topos. So you can make the definition. Let's see. Cohomology of X with integral coefficients is one way to say it in terms of the formalism that I now introduced. You take the X groups in light condensed abelian groups. Actually, they would also be the same one as in all condensed abelian groups. Well, it could. I'm doing light stuff, so let me assume it's light. Of the free guy on X against M or M under. Sorry, this was coefficients. Right, so this is. When you work on the étale topos, these are the étale cohomology groups. When you work now, condensed topos, these are, I don't know, the condensed cohomology groups, whatever you want to call them. And you, like, if the series should behave well, this should recover the right cohomology for like manifolds or something like this. And it does. So that's the theorem. If say X is a CW complex, this thing is exactly, or it's underlined, it's exactly the singular cohomology. And a priori, this might seem a little bit weird because we didn't really put any geometry into the definition of these condensed sets, right? We were just using totally disconnected things. And suddenly, using totally disconnected things, we're still able to probe whether like that circle is not contractible. but it comes out right. And right. So let me actually recall that. I mean, yeah. Let me make one remark about this and then stop. So as I said, this is here the of these X groups. And I told you how to think about this, right? So this was the thing where you take finite sums of X, points of X, valued by integers. And so this is actually, I mean, there's a Stoll-Thom theorem, which basically tells you that this guy is something like a model for the homology of X. Once you treat this somehow up to homotopy equivalence, this kind of guy is a model for the homology of X. And well, for us, the interval is in condensed sets is like an actual interval. It's not a point. So we didn't yet pass to homotopy. But one way in which you're doing that is somehow by taking X groups out of it, because the interval cannot somehow map to something discrete abelian group. And so yeah, so this dualizing, I mean, this is like homology, so the dual should be like homology, which fits the picture. And yeah, let me just stop here. Other questions?
If you use the internal X, you recover the higher direct images.
All right, so we can also consider the internal X here. In this case, this will just unravel to some adjunctions to also replacing M by the continuous functions from S into M, which is still a discrete abelian group. So it doesn't really know that much more. Maybe one comment to make is that, and maybe I won't talk so that much about it, but for all sorts of things like continuous group cohomology and so on, sometimes it's not quite clear, like what is a continuous representation of a group, what is the right notion of continuous group cohomology, because often this is just represented by some explicit cochain complex. But if you just treat your topological groups as condensed abelian groups, then it's clear what an action on like a condensed abelian group should be. And it's clear what cohomology should be, just there's some kind of general topotheoretic answer to what it should be. And this always gives you the expected answer. It's not always the same thing as the thing computed by continuous cochains, but when it's not, it's a better answer.
So here, when you have a CW complex, if you have more generally a local system, I think it will give a shift on condensed sets over X underlined. And then you can say that the usual cohomologies like singular or shift cohomology, it satisfies cohomological descent for,
yes,
like in a, for at least for compact Hausdorff spaces, it satisfies cohomological descent for surjections of compact Hausdorff spaces. So to compare the two sides, somehow it looks like using the theory of cohomological descent to well, essentially to do the, it should give
yes,
an,
exactly.
to do it with local systems by.
Yeah, you can use any coefficient system really on X, and this is good. Yeah, it's a really robust result. But if you, for example, work in like this sequential topos where you only allow n union infinity as your generating object, then if you would try to compute this cohomology of like the interval, then you would first have to express your interval in terms of your generating object. So we would write this as this huge co-limit of all these small countable closed subthings in the interval. And then this cohomology would turn this huge co-limit into a huge derived limit. And I can't exclude the possibility that it comes out right, but I think it's extremely unlikely that it will come out right and produce the expected answer. So, and this is, Yeah, that this is true is really an indication that it's a good framework. Anyways.
But do we know the category of light condensed abelian group has enough projective objects?
Light condensed abelian groups, whether they have enough projective objects, they don't, unfortunately. It's one reason we were a bit hesitant to make the move, but in the end we realized it's not actually that important. So yeah, so I don't think you can, if you take the free condensed abelian group on the counter set, I don't think you can find a projective cover of that.
Okay, so.
But you can, I mean, in practice, one thing you can do is embed light condensed abelian groups into all condensed abelian groups, which is a function that preserves all colimits and all countable limits. So it's compatible with a lot of operations. And then in there, you have enough projective objects. So for example, if you want to do some computations, you could always work in the larger category and do the computations there. Any further questions? That doesn't seem to be the case, so let's stop here.